All right, so hi everyone, welcome to section. Let's see, I think midterms were released last week. If you have any questions about the midterm, feel free to email me and we can set up a time to meet, okay? Cool, let's see. So now I'll be going more towards like live coding, and so I'll write stuff on the whiteboard, but then after we get like some of the intuition down, then we'll start writing pseudocode and the actual code on the screen, okay? Just because it's faster. Yeah. All right. Just course registration opened last night, and I just wanted to give a quick promotion of 106L. So remember, 106L is the advanced C++ class that you can take. I'm teaching it next fall. I'm going to co-teach it with another section leader, and we're going to be doing a lot of cool stuff. For example, let me quickly switch to the screen. For example, we are making slides for for streams right now, and you can see like, oh, there's a lot of really cool slides going on. I spent a lot of time making these slides. Right? And then like in this class, you don't really learn too much about streams other than how to read and write from them. So if you want to learn much more about like streams and essentially all the other topics in the class that we don't really cover, take this class. It's 1 unit pass-fail. It's really chill. Okay? Cool. Yeah. And you get the colorful slides as well. All right. But enough 106L promotion. Let's get into linked list material. So linked lists, the first question we're going to cover is called isSorted. All right, that's question 2. You don't have to read the question. It's fairly straightforward. The question is asking whether or not, given a pointer to a linked list like this, figure out whether or not the list is sorted. Okay, isSorted is defined as non-decreasing order. So for example, 3, 4, 4, 5, that is not decreasing, so that is sorted. We say this is sorted. This would be true. This should return true. This is not in non-decreasing order because 3 decreases to 2, so this is false. False. Okay. We have to worry about these 2 edge cases, which is just whether or not, if you have an empty list, is it sorted? And I think this we count as is sorted because it's like vacuously true that if you don't have any elements, then all the elements are sorted because you don't have any elements. Okay, so we say this is true. And then anyone want to take a guess? Is this list sorted? Yes or no? Yes, okay. If you have 1 element, we just say, oh yeah, it is sorted. It's not in the wrong order because you only have 1 element. Okay? Cool. So we're going to try to solve this question, and we're going to try to, that's not insert, that's isSorted here. Okay? We're going to try to write code, which is essentially we're going to go through the entire list, figuring out whether or not it's sorted. Okay? All right. So any ideas on how to tackle this question? We have to go through the entire list. Right? How can we do that? We have to loop through the list. Mm-hmm. How can we loop through a list? Yes?
We can make a temp pointer.
Okay.
And then you can continue. I don't know.
Sure, yeah. That's a good idea. So we're going to start, let's zoom in a little. We're going to start by making I usually call this current because it's the pointer, which is going to start in the front. It's going to start in the front, so cur starts in the front. And then we're going to move it down one by one so that it can essentially go access all the elements. Okay? I think you've seen this in lecture a lot, which is you're going to start in the front and go through all the elements. Okay? You don't actually want to element front or front itself, because if you modify front itself and then later on you figure out you need the element in the front again, once you change like this pointer, you can't ever access this element back. Okay? Does that make sense? If I change this pointer to like here, then there's no way I can access this pointer. So usually you don't want to change front. You just want to create a temporary pointer to move it down. All right? Okay. And how do we move this pointer down one by one through each element? Yeah?
I'll just point to the current current.next.
Sure.
And until it points to now.
Okay, so while I'm not going to put the something in first, but while something, we're going to essentially make it keep going down. So while that, we're going to cur equals cur next. Okay. So yeah, this is often, we're going to keep going. Each time we're going to move cur to its cur next. So for example, here, cur is pointing to 3, and cur next is 4. So cur equals cur next. What that does is it sets cur equal to cur next 4. Okay, and it's going to keep doing that, and it's going to go one down, one by one by one. Okay. Now, before we get to that point, I want to talk about just a general linked list strategy, which is when you first look at a question, think about how you would deal with the elements in the middle. All right, ignore the front, ignore the back, because those usually cause tricky cases. But first, think about if you have just generic elements in the middle. So what does that mean? Usually that means something like, oh, look at the elements 4, 4. Okay, sometimes 4, 5, 4, 4, 3, 4. How can, if I just gave you two generic elements like A and B, what should you be doing checking to them to see if the list is sorted? How are we checking if the list is sorted? Yeah. Mm-hmm.
Yeah.
Sure. Yeah. So essentially, we're going to go through the list, comparing one pair by pair by pair, right? If you ever see a number that's the number in the front is greater than the number in the back, that means it's not sorted, right? If you ever see something like this, then it's not sorted. But if you keep going and you're just like, okay, this is less than or equal to that, this is less than or equal to that, this is less than or equal to that, then you know that it is sorted. Okay. Yeah. So we often have to do. Let's see. Before here, let's pretend that we have like an A and a B. Okay, if you just take any two generic elements, we want to check if A is greater than B, then we know that the entire list is not sorted, in which case we just return false. Okay, and then we're just going to keep doing that. Check this is A, this is B, check it, A, B, check it, A, B, check it. Okay, now at this time we want to think about, all right, we're looking at pairs of elements at a time. Where should our loop go up to? Because our loop is going to start in the front, right? But when should the while loop stop? It should keep going, but when should it stop? Yes?
Null pointer.
When cur next is null pointer?
Yeah.
Yeah. Okay. So we want, let's see, the code here would be cur next is null pointer is not equal to null pointer. And the reason for that is here, we're considering pairs of elements at a time. So if we're thinking about cur right now, so this is cur, then we're comparing cur to cur next. That's a pair. Cur to cur next, cur to cur next. Okay, so when cur is finally here, so cur and cur next, and then when we try to increment that one more time, at this point we should not try to compare cur and cur next. Because if you do that comparison, you'll get cur and cur next doesn't exist. Okay, if you try to do that, it's going to crash. So rather than try to compare cur and cur next, once cur reaches the last element, so that's when cur next is null pointer, then we should stop. Okay. Another way to rephrase this condition is while we are not at the last element. Okay, because once you're at the last element, there's no point in comparing to the next element after that, because there's no next element. Okay, if I told you that this is less than this one, this is less than or equal to this one, and this is less than or equal to this one, you don't need to do any more comparisons. You know that it has to be true. There's nothing more to compare. All right, so that is why we do this condition up here. Oftentimes, when you write different kinds of code, you'll often see two different kinds of loops. One is while cur is not equal to null pointer, and then the other is while cur next is not null pointer. Okay, and this is like precisely one difference why we use them, which is we use this one when you're comparing like pairs of elements. Whenever you need access to like two different elements at the same time, you want to make sure that you don't go off past the end of the list. Okay, while in this example, if you just need access to one element at a time, and you don't have to ever change any elements, then you can just use the first one. Okay, all the examples we're going to do today are going to use this one because this one's a little harder to deal with. And whenever you have to insert or remove something from a list, think about how you're going to insert or remove something, right? If I want to say insert an element over here, you have to change this pointer over here. Okay, so because of that, that's why we often want to make sure that we have access to both two elements at the same time. We use the bottom one. Any questions at this point? Yes, question.
Case when it's just like like in the, I guess the input part, the like pointer is a null pointer.
Yeah, that's a great question. So the question was, how do we handle the case when the front pointer is a null pointer? And yeah, that is definitely one case that you should think about when you're done writing the generic what happens in the middle. Then you should start worrying about, okay, what do I do in the front? Does it work? If it doesn't work, you have to write code to fix that. Does it work in the back? If it doesn't work, you have to write code to fix that. Okay, and part of that would be, okay, what if the front is null pointer? Then we have to check that. Okay, yeah, so that's a very good point. I'm gonna write just a note at the very top. We'll handle this last, which is remember to handle when front is null pointer. Okay, now how do we convert this check into code? So here we know that A is just cur, and then our B is cur next. Okay, how do we check this condition? If A is greater than B, return false. Yes.
If cur data is greater than cur next, then
Yeah, exactly.
return false.
Great. Yeah. So remember, cur and cur next themselves are pointers. To get the actual number that they contain, you have to use arrow data one more time. All right. So this is checking if the current data is greater than the current next data. If that's the case, then it's not sorted. So that means it's not in non-decreasing order. Ooh, double negatives. Not in non-decreasing order is not sorted. Okay. All right. Anything else you have to deal with? Okay. So yes, return true. So if we pass the entire loop, yeah, so I think you mentioned return true. If we pass the entire loop, so we keep going, we keep doing this check, but we never return false. When we reach the end, that means, oh, it is sorted. So we just return true. Okay. Let's run this. It's not going to pass. It fails one case. And that one case is exactly the case you mentioned, which is, okay, what if our list over here is the empty list, which means we have the null pointer. Oftentimes in linked list questions, you will have to do that check separately in the front. So here we would say if front is equal to null pointer, then return true. Okay? Yay. All right, any questions at this point? Okay, let's go to the next question. Let's do insert. So insert is, this is a very common thing that you'll have to do for linked lists, and that's given a list, add a new element in there. Okay, so let's write it out. So suppose you were given this list. Let me rename this as front. Okay, and what's going to happen is you're going to be given the pointer to the front. You'll also be given an index. Let me check my header. Index and value. Okay, so you're going to be given an index. The index is essentially what index you want to insert into the list. Okay, we use 0 indexing as always, so this will be index 0, this will be index 1, this will be index 2, this will be index 3. Okay, oh, and there's also an index 4. Okay, this is just like how you would insert into a vector. Right, when you insert into a vector, you would add it into these places. And for this question, we don't have to do any error checking. Now, on your assignments, you should do error checking because you can't guarantee I'm not going to say insert front 10. But in this question, we're just going to keep it simple. We're not going to do any error checking. Okay. All right. Let's see. So yeah, you're going to be given an index. Let's just say 2. And you're also going to be given a value. Let's say 6. Okay. So what should happen here is I would want to insert a new node at index 2. So instead of just this link over here, I'll have a new node 6. And this should go between these two. Okay? Does the question make sense? Okay. This is a very common thing you'll be doing for linked lists. Now let's try to write the code for that. So let's think. Okay. So when when you want to write code to do that, to insert something into a list, all right, if you just look at this diagram, what pointers do you have to change? There are a couple pointers you have to change. Which ones?
The first four.
This one?
Needs to move to 6.
Yeah, this one to 6? Okay, yeah, so one thing we have to do is we have to change this pointer to 6. So we're gonna have to do something like this. So the 6 is now part of the list. And then there's one more pointer we have to change. Yeah.
You have to make the 6 go to the 4.
Yeah, 6 to 4. Okay. So this is what we're doing. We're just trying to like insert this thing into the list. So if you move this up here, it's now part of the entire list. Okay. All right. Before we do that, let me erase this just so we know we can write code for this step by step. When you do pointer questions, always draw pictures like this, and then you can do like step by step. Okay, I write a line of code that changes this pointer. I write another line of code that changes that pointer. Okay, that's the key to success for assignment 6. Don't try to visualize everything in your head. All right, let's see. Okay, so now that we know how to like add something, but the thing is we have to figure out like where we have to add it. Right? We don't have access just to like these locations. How do we access where to insert? For example, if I told you I want to insert at index 2, how do you come to this location? We don't have access to this location. Yeah?
You might want to like go through 2 nodes.
Okay, yeah, so essentially we can only start from the front, and then here you would want to go to like move forward until you get to here. Okay? Now here's this thing, so apparently Tyler didn't mention this. This is called the James Bond analogy, and I'm going to try to explain it right now. Okay? So when James Bond, so I've never watched the movie, so I have no idea what this means, but apparently when he tries to detach cars from trains, apparently he does that. When you detach a car from a train and the front of the train is over here, if you want to detach like the rest of the train from the front, you have to be standing before the link you're trying to detach, right? If this is a train moving that way, if you wanted to detach this part, you should be standing here to detach it. Right? If you're standing here and you detach it, well, you will be lost with the rest of the section. So you have to be standing before that chain. Okay? All right, apparently no one thinks this is interesting. But yeah, this is called the James Bond analogy. If you don't remember, just remember you have to be standing in the front. Okay? So here, this person is Kerr. Our Kerr has to be here. And the reason why that is we need to be able to change this pointer. And to be able to change this pointer, we have to have Kerr pointing over here. Okay? If Kerr is already pointing over here, then we can't change this pointer. Okay? So we want to move Kerr all the way up to over here. How can we move Kerr starting from the front over there? How do we do that? So Kerr starts at the front. How do we move it down to that location? Yeah, so we want to essentially move it forward index -1 times, right? Here, we want to move it forward 1 time. From the 3, go to the 4, and that's index 2, so index -1. Let's declare Kerr equal to front. And then how do we move it forward by index -1 times? Yeah? Yep, use a for loop. And I equals 0, I is less than index -1, I plus plus, and then just every time in the loop, you just move it forward by 1. So Kerr is equal to Kerr next. Okay, great. Yeah, so that moves the Kerr pointer over forward to 4. And then now let's go back to the step-by-step. There were, I think, 3 things you had to do. 1 was make this thing. 2 was change this pointer. And 3 was change this pointer. Okay? How do we do that in code? Yes? Link the 6 to 4. Okay. Okay, so you're saying link the 6 to this 4.
Yeah.
Then link the 4 to the 6.
Yeah.
Yeah. Okay. Yeah. That's a really good suggestion. So remember, we want to do this link first before we do this link, because if you do this link first, then you kind of lose the 4. Right? Once you change this pointer, you can't ever go to the 4 again. The 4 is kind of lost. So the order in which you do the statements matter. Right? We want to first change this link to 4. Before we do that, we need to first create the node. Do you remember how to create the node? How do you create a new list node? New list node. Okay, yeah. So remember, creating a new pointer, you just declare the pointer as like over here as on the stack. But when you're creating a new list node object, you have to create it on the heap. So that's why we have to use the keyword new. New list node, you can treat this as a constructor as well. So you can pass it different parameters or parameters in the constructor, which will automatically fill data and next. Okay, so for example, here you mentioned you wanted to connect 6 to 4. So I can just simply say, okay, I want the value 6 in our list node. What should 6's next point to? It should point to the 4. How do you get the 4? Yeah, cur next. Cur next. Okay, so the 6 is the value. Oh, not a 6, just the generic value we passed in. And then we want this list node to point to cur next. This points to cur next. Okay, so that's what that one line of code does. All right, and then how can we change the 4 to the 6? How can we do the cur? How can we change this one to point to here? Which pointer are we changing? Cur next. Okay, and we want to set that to 6. Yeah, so we can do something like this, cur next, and then we want to set that equal to the new something, okay? So remember what new does is new creates the object on the heap, and what it also does is it returns the address or the pointer to that object, okay? So when you say new list node 6, you create this object, you also return a pointer to that object. So when you set cur next equal to that, you're setting cur next equal to the pointer to 6. So we're setting this equal to a pointer to 6. Okay? Yeah, so this line of code over here is tricky. It's doing 3 things at the same time. It's saying, okay, create a new node, set that new node's next to cur next, and then reassign cur next to be pointing to that node itself. 3 different things that line is doing. Okay? One question you get is, okay, wait, I'm using cur next, but then I'm reassigning cur next. That's kind of confusing. And this is fine because we evaluate like right to left. So we're going to do this line first. And then after we use cur next, then we can reassign cur next. Okay, does that make sense? Okay, what questions do you have at this point? Question? Yes?
Things to check.
Okay, what to check?
Like cur next in the loop and in the new line. We both need to check cur next.
New line. Okay, so where? Where should we check?
So we need to make sure not cur next. Like in the loop, we need to check that cur is not a null pointer.
Mm-hmm. Oh yeah. Okay. So yeah, we can do that. Although the question says we don't have to do any error checking.
Oh, sorry, I didn't see that.
Yeah, that's fine. So yeah, we don't have to do any error checking. But if you wanted to do error checking in this question, you'd want to essentially check. Okay, every time you move forward, you want to make sure that there is a next element. Okay, so you would check something like, if cur, or before you do the cur equals cur next, you want to check like, if cur is equal to null pointer, then throw out of bounds, index out of bounds, something like that. Okay. Yeah, this would be error checking. Okay, anything else with the handle? If I run this, this will pass most, but not all the tests. Yeah. Okay. Can you see specifically which tests it's not passing? It's specifically failing the index 0 tests. Okay, and here's the common thing you have to do for linked lists. You first worry about the logic for the middle, because that's the most important part. But you should also think about what happens at the front and the end. Okay, specifically here, the front doesn't work, and let's look at why. The front over here, if we put index is 0 here, then the loop doesn't run, and then we just set cur next is equal to new list node. So what this is doing is if you say insert at index 0, it's actually going to insert index 1. Right? Index 0 and index 1 right now in the code does the same thing. It's just skipping the for loop and it's just adding something at cur starts in the front. So our person is over here. And we're setting Right now, both index 0 and 1 are going to add the pointer to this place, which is why, did they show an example? Yeah, if you look at this example, the expected is 33 should be added at index 0, but instead we're adding 33 at index 1. Okay, do you see that? Yeah, and then the reason for that is because when index is equal to 0 or 1, it's doing the same thing. It's skipping the for loop and it's setting cur next equal to that. But instead, if we're inserting at index 0, we want to change, what pointer are we changing to add at index 0? Front, right? We have to change front. Front is a little different from all the other pointers, right? Where here we have to actually change front itself to add at index 0. Okay, so how we do that is let's make that a special case in the front, which is specifically if you want to add at index 0. So if index is equal to 0. Okay, how do we add at index 0? Let's add a new node here. 7. Okay, how do we add at index 0? Yes.
List node, and then we said like the first part of the value and the second part is just the front.
So we set this part over to here. Okay, great. And then there's one more thing we have to change. We have to change front itself. So I'm going to change this arrow and make it point to here. So, kind of like this line of code over here. It's doing 3 parts at the same time. We're creating the new list node. We're putting the value there. But instead of just cur next, we want the new node to now point to front because we're inserting an index 0. So the next node after our new index 0 should be the front from before. So we're putting front over here. And then we have to also change front. This node is the front node, so we're setting front equal to that. Okay, and then after that, just make sure you return, and this should pass. Yay. All right. Any questions? All right. One thing to think about is now notice this, okay? This is really interesting. I have this ampersand over here. If I remove the ampersand, something bad's going to happen. Oh. If I remove this ampersand, it doesn't pass these cases. If I put the ampersand back in, the ampersand here, let me zoom in, this ampersand over here, this ampersand over here, if I put the ampersand back in, this works. Can anyone see why? Why is that ampersand important? So if you went to section last week, which none of you did, but if you went to section last week, you'll know that when you pass a parameter, when you pass a pointer into a function, by default, it's passed by value. Right? When you pass a pointer to a function, you're passing it by value. When that happens, let me draw it out. So here's the heap. Here's the stack. Okay. So suppose I had a main function, and I created a list. So list node front is equal to something, and then I passed it into insert front 0, 6. Okay. So when I write this line of code, let's see, front is currently, so front itself is a pointer. This is in main. Front is a pointer, which points to some linked list here. Okay. When I pass it into the function, I create a new stack frame, and then I get front is the parameter, so I get a front parameter. And because it's passed by value, if I pass it by value, what happens is I'm going to create a copy of it, which still points to the same thing on the heap. Okay. Now, so I can go to front next or whatever and change the stuff here, right? Which is why all the other tests pass if I don't put the ampersand. But the thing is, if I try to change front itself, which I'm trying to do in this function, if I change front itself, let's say I created another node. This node points to here, and I changed front I said front equals new node. I've changed front to point to here. Right? Notice what happens when this function returns. Our list originally is still pointing to the old list. It's not. This front is not changed to point to our new list. All right? Does everyone see the issue? This is why we have to pass it by reference, because if you ever have to modify front, the pointer itself exists on the stack. So if you pass it as a value, it's not going to change the front from main. But if you pass it as a reference, then what happens is then front is now a reference. This is a reference to this thing over here. I don't want to use arrows. This is a reference to star. Star is this thing. So any change you make to front here will change the front here. So here is where, when we try to do set front equals new node, this works. Okay? Yeah, this concept is super important. Why do you have to pass the pointer by reference? Right? And the key thing to note is you don't always have to pass it by reference. Like, notice in isSorted, we did not pass the pointer by reference. All right? And then the time where you do need to pass it by reference is when you actually modify front. Okay? Not front next. If you modify front next, that's totally fine. But if you ever have a front equals something, that means you're modifying front and you have to pass it by reference. Okay? Any questions? Yeah, so what I always remember, especially when I look at code, I just look, okay, is there a front equals something? If there is, add the reference. Okay, now don't just blindly always just put the ampersand in there. Actually make sure you're changing front before you add the ampersand. Okay, all right, any questions? All right, let's see. Let's do this function called removeAll. And I want to do it in two ways. One, I want to do it iteratively, so just like what we've been doing so far. And then another way, I'm going to be doing it recursively. So linked list questions, they're really fun to do recursively. So I'll show you how to do that recursively. Okay. I highly suggest you do this question called split. Split is kind of a question which is kind of on the difficulty of like an exam question. So when you have time, I encourage you to do split, which is the last question on the handout. Okay. If we have time, we'll get to split, but I don't think we'll have time. Okay, removeAll. Let's try to do removeAll. So removeAll is fairly straightforward in terms of what it's doing. removeAll is similar to the question we've been doing right now, but instead of adding or inserting, we're removing stuff. So let's see. Front is now pointing to, let's say, 3, 5, 5, 7. And then a call to removeAll front of, and then we give it a value 5. What this should do is it should go through front, and it should remove all the nodes with 5 in them. Okay, so in this example, what you'd want to do is you want to remove this one, you want to remove that one, and you want to make sure the rest of the links stay correct. Make sense? Okay, so just like in the previous questions, we want to first think about how do we handle the nodes in the middle? Okay. Before we get to that, any ideas on how to approach this question? So what should the first thing we do be? How do we access the elements in the middle? So kind of like the previous questions, we have to go through the elements inside our list. All right, we have to go through them one by one to see if they match value. So to do that, we have to do a while loop. Right? And then here, kind of like the James Bond analogy again. If we want to remove 5, we have to be standing in front of the 5 to be able to change this link. So here's a case where we do actually have to do the same thing. We have to move. We want to essentially stop when we reach the last one. So cur next is equal to null pointer. Oops, goals equal. So we want cur to keep increasing until cur next is null pointer. Okay. All right. So what do we do here? Cur is moving forward. Cur equals cur next. Cur is just moving forward, but what should happen as it's moving forward? if.
Check to see if it's the value that is like given to remove.
Yeah, exactly. So we want to check if, should we check cur or cur next? Yeah, we should check cur next, right? Because cur is the one before. So that's the one we have to modify to remove cur next. So we should be checking cur next. Cur next. And then we get the data. Check if that's equal to value. If it is, then, so let's say cur is over here. This is cur. And we find that cur next is equal to 5. Okay. A couple steps. How do we remove the 5? Yeah. Mm-hmm.
You just cur next equals to cur next.
Okay, so we can do cur next. So this pointer is equal to cur next, which is here. So that does this thing. Okay. All right, yeah, this is good. One thing to be careful is now we've like lost this one. Remember to free the memory. So we have to first free this memory as well. Okay, yeah. So yeah, this is really close. But before we do this line, we're going to do this line next. But before we do that, we have to first deal with this one. How do you deal with this one? Yeah, exactly. So once you change this pointer, you can't access this one again. So let's just declare a temp. I personally like to declare this one as called trash because it literally is trash. We're going to delete it next. So I personally call it trash. So let's see. List node trash. That's equal to cur next. Okay. Actually, the video is showing here. So the pointer is still here. And we're saying, okay, trash, set that equal to cur next. So this is trash. Now we can change this pointer to point to here. Okay. What pointers do we have to change to do that? Cur next. Okay. I'm going to set that equal to. Yeah, or shorter trash next. Okay. Great. And then one more step. What do we do with trash? Yes, we have to take out the trash, delete trash. All right, so that deletes the trash, and then that deletes the trash. Oh, you mean like this? Yeah. You use delete square brackets when you're deleting an array, when you're freeing an array. Yeah, here we're dealing with like individual objects, so we can just use delete. Yeah, the nice way to remember is anything you create with new, you just use delete. But if you use new, like something bracket, then you have to use delete bracket. Okay? Yeah, super important on assignment 6. Every time you use new, you should use delete in the same way to free the memory. I want to make sure there are no memory leaks. Okay, what else? One thing to worry about here is we're setting, right now we have cur equals cur next always. So after this line is done, we shouldn't be moving cur. Right, if we move cur, so suppose we decided to move cur. Oh, I'll put the person on the top. If we moved cur, then notice what happened, right? We never got a chance to actually delete 5. The pointer has to be standing on the previous one. So it's not in all cases we should move cur forward. We should only move cur forward when, specifically in the case when we remove a node, when we decide to delete this node, we shouldn't move cur forward, right? Because we need cur. Cur next is now pointing to a new element that we haven't checked yet. So in this case, cur shouldn't be moving forward. Cur should only be moving forward when you checked that the next node is fine. Okay. Does that make sense? This is kind of like when you remove an item from a vector. You have to be careful about the index. Like if you were trying to write remove all from a vector, once you remove an element, you shouldn't keep moving forward because all the elements have shifted down by 1. In this example, once you remove this element, cur next is pointing to a new element that you haven't checked yet. So you have to stay here, check that element before you move on. Okay? Does that make sense? Any questions? Should I explain that one more time? Should I explain it one more time? Ooh, I haven't do the chair. Should I explain it one more time? Or we're all set? Okay. So here, here we should not change cur, but we should change cur if we checked that element and it was not val. So we add an else statement here. Okay, and if we run it, it's going to pass like 4 out of 9. Yeah, there we go. So okay, so it doesn't quite work yet. Can anyone see the issue? Let's see. Which tests are we failing? Yeah, so this is not correctly removing from the front. All right, yeah, this is still also, we can't remove from the front, can't remove from the front, can't remove from the front. So here, we also have to do that special thing. We have to make a special case to handle the front. Okay. The question is, where do we handle the front? Usually we do the before we do the loop. But the thing is, think about what happens if you try to handle the front before we do the loop, right? Let's write a new example. Front 5, 6, or actually let's do 5, 5, then 6. Okay. Suppose we try to handle the front. Then what we'll do is, okay, we'll remove this one, and then we'll change front to here. That's also a problem because now, we have to handle front again. Right? We can never actually go into our loop because our front keeps changing. But even while front is changing, we can't go into the loop yet. We have to handle front as a special case. So what is a better way to do this? Let's let the loop run first. When the loop runs first, it's going to free everything after the front first. So it's going to remove this one. Only after you're done should you go back to the front and change it if necessary. Does that make sense? So right now, if you look at the code, everything is correct. Like here, the 12 is correctly removed. Everything is correct. Here, everything is correct except for the front, which means at the end of freeing everything, we can just go to the front and remove it again. Does that make sense? We don't want to do that removal first because that kind of messes up everything starts shifting up, and then we have more fronts that we have to deal with. Rather, ignore front first, free everything else, then come back to front if necessary. Because once we come back, even if we change front, all the other ones have been freed already. So we're just going to go to the end, and we're just going to say if front data is equal to val, then kind of the same thing we did up here, right? If front is equal to 5, then which pointers do we change? We have to change front to point 2 here, or front to point 2, whatever the next is. So here the next was this one. We want to change front to point 2, front next. But before we do that, we have to do trash of this one. Then we change front to here. Then we delete the trash. Okay, so kind of like what we did above, except now we're doing it with front. So here we do list node trash equals front equals front next, and then delete trash. Okay, submit, and it's going to pass. No. Oh, yeah, okay. Okay, so right now, any questions? All right, so any questions right now? No? Okay. Two things to point out. First is, as you see, there's a test that fails, which is the null pointer. You should always just check, before you do anything like cur next, you want to check if the pointer that was passed in was null pointer. If it is, then just don't do anything. Okay, and that will pass all the cases. Yay. Other thing to note is, all right, can you think about why we're passing ampersand here? If I remove the ampersand, then it's going to fail the same test that I failed. Right, before it was 4 out of 9, but this one now passes, so that's 5 out of 9. Why do we have to put the ampersand here? Yeah.
Because we're modifying the front.
Yeah, because here we specifically have a front equals front next, so that is modifying the front. Okay? Anytime you have a front equals something, you have to pass it by reference. Okay, any questions? Okay, you'll be doing this on assignment 6, so this code and the insert code is a good one to review because you'll be doing something really similar in assignment 6. Okay, before we go on, let's do this recursively. Okay, I really like doing linked list questions recursively because the solutions are often really short. The thing I don't like about iterative solutions to linked lists is that you often have to like, cur often has to be one step away from the thing you're actually modifying. So you'll be having a lot of cur next data, cur next data, cur next data. It's kind of annoying, okay? And the thing is, you're always thinking, okay, my while loop, is it gonna go correctly? Is it gonna go correctly to the end? It's hard to remember exactly. It's hard to catch all those edge cases. So what I like to do about it recursively is, let's try to think about how to do this recursively. Okay, so recursively, why linked list questions are good to do recursively is because linked lists are, if you just look at a linked list, it itself is very self-similar. 5, 7, 5, 8. Okay, if you look at a linked list, it's very self-similar. Specifically, what aspect of it is self-similar? If I told you this is a linked list, can you find a smaller linked list within this large linked list? This whole thing is a linked list. A linked list has a smaller linked list within it. Right? I could say, okay, I'm going to give you this pointer. And this is a linked list as well. Does that make sense? So this is why I like to do linked list questions self-similarly. If you did binary search trees today, you'll also see binary search trees are self-similar. Okay? Okay, let's think about how you would remove all from recursively. Okay? So if I said remove all 5, given this list, how can you do this recursively? If you want to go back to how you did recursion, pretend you have a remove all light, which removes any linked list that's smaller than the current linked list. How can you do this recursively? Any ideas? Yeah. Ideas? As a hint, you want to do as little work as possible, right? So as little work as possible, focus on the first element. Okay, so let's see. Let's focus on the first element. If the front is equal to front data is equal to val, then you know that, okay, you have to delete the front. So let's say list node trash is equal to front. Okay. So suppose we now have trash over here. We're going to delete that later. How do you remove all from the rest? Yeah, we just call the function again, right? So we can say remove all. But what do we pass into remove all? Front. Yeah, we can do front next, val here, then we can delete trash. Oh, if that's the case, then we don't need this. We can just do delete front. Well, actually, I don't like that. Let's do list node trash is equal to front. We change front equals to front next, and then we change this to front. Okay, so just a slight reordering. Trash is this one. We set front now to here, so now its front is equal to this one. Remove all from that, and then be sure to delete trash. Okay, at the very end of this function, front is still going to be correct. It's going to correctly point to the remaining of the list. We don't need this element anymore. Okay, does that make sense? Should I explain this one more time, or are there any questions I can answer right now? Yeah, so let's see. When you're changing it inside remove all? Line above? Here, okay. So this one? Okay. So here, let me walk through step by step what's happening here. Okay, front was before pointing to this. We're saying, okay, the first line that we do is to call this trash. So we're going to call this one trash. I don't have a delete yet. I need to write a delete. But we call this one trash. Then we set front to equal front next. So front was before this, so front next would be this one. We want to set front to be equal to front next, which is like this. Then we make a recursive call on front, which is going to remove everything from here. It's going to remove all from the new front, which is going to be everything else in the list. So you can trust that it works. It's just going to remove this one. At the end, front is still going to be correctly pointing to the new list that you should be returning, the final result. And just don't forget you have to call delete trash. Okay. Almost out of time, but I just want to quickly mention, okay, what if front is not the element? So what if we have this example, front is pointing to 7. How can we use this recursively? Front, so we don't actually want to change front. Front should still stay at 7, right? Because at the end, front should be pointing to 7. So we don't want to change front, but we do want to be able to recursively remove everything else. How do you do that? It's called remove all. We know that the front works already, so we can keep front, but we want to remove all of front next. Okay, let's run that. Oh boy. Oh yeah. We're missing one thing. We don't have a base case. This is all the recursive case. We need a base case. When should the recursion stop? Yeah, front is equal to null pater. Oh yeah. None of you were here last week, so you don't know my null pater joke, and you never will. All right, and we pass. Okay. Now this is tricky code. This is I like writing this code because I have a lot of experience with it and it's really short. So I like writing like this. But this code is often hard to figure out. So you can write it on your assignments if it's clean and if you would like to think recursively. Although I suggest if you're doing the linked list for the first time, I recommend using a while loop to go through it. Okay. On the exams, the iterative approach oftentimes is really long, but if you do it recursively, it's really short. Okay. Unfortunately, recursively, it's also easy to mess up if you forget. Like if you just forget a base case, the whole thing blows up. Okay, any questions I can answer right now? Okay, assignment 5, please, before 5 p.m., please check it very carefully. The test cases we give you are not exhaustive, so you should do your own testing, okay? I want everyone to get a check plus, partly because I want you all to do well, partly because I don't want to debug PQ. Okay, debugging PQ is like the worst. I spent 4 hours in the layer last night, so please make sure you test your PQ very carefully. The test cases are not exhaustive. The test cases we gave you, the 4 inputs, they're not exhaustive. Okay? In particular, I want to point out one test case, and that's this one. One thing you want to be careful of is suppose you had a heap which looks like this. 2, 4. And if I told you to bubble this item down, you'll be swapping with this one. Well, you'll be swapping with, let's see, this is 3. You'll be swapping the 5 with the 2, then the 5 with the 4, right? But one thing to be careful of is you don't actually, when you're bubbling down, you should be comparing to 2 children. Sometimes you don't have 2 children. Sometimes you only have 1 children. So you don't actually have a children over here. Okay? You have to check for that. Don't just blindly say, okay, I'm gonna check both children, even if that one doesn't exist. Okay? It might not crash on your computer because this is technically undefined behavior, but it will crash when we test it. So make sure you check that the children actually exist. Don't just assume that the children is there. Okay? All right. Thanks for coming. I'll see you next week.